I assume you're all here by mistake. Seriously, do you want to learn about DFU, the file utility from Bradley Custer? It's way more useful. You will use DFU way more often than you ever learn anything from here.
I'm shy, John.
I am shy. So part of this, when they're collecting, abstracts for talks for the bootcamp, Camille's asking for, we want some more technical stuff, not, you see a lot of directions and stuff from Camille and about the future and roadmaps. He said, how about back to the old digital days, ones and zeros? And I said, I can talk about things that we did in the compilers and the calling standards. You're my compiler talk. I can show you little boxes and pictures and arrows. You can be impressed by boxes and arrows, but it's like, we actually did stuff, right? It's like, it took a long time to put all these pieces together to make VMS handle things that are coming from a Linuxy type backend, because we didn't want to make things digital only again. We didn't want to have our own calling center again. I wanted to use the industry format of everything to make it easy to take, again, Linux objects, Linux things, bring into VMS as best as possible. So I said, I can show you behind the scenes. Here's what we did. Here's some changes. I can show you where it might impact people's programs. There's a few places that you might have to change your code. This is, if you have a condition handler and look at registers and do things and dump things out, yeah, this might be interesting too. But the rest, just take a rest and. So again, one of the things for picking a calling standard on every platform, the compiler has to decide how parameters are passed from routine to routine. Are they passed on the stack? Are they passed in registered? How many? Which ones? On VAX and Alpha, the calling standard and the hardware, they kind of work hand in hand. On Titanium, we were kind of stuck with, we used the actually industry Intel calling sequence. That came with the Intel compiler backend that we use for Intel C++. So we picked that, but for x86, what can we pick? I said, well, we're not going to do our own. I don't want to do that again. So I can either pick the Windows one or the Linux one. Well, given that we're so Linux focused, I want to make VMS look, I'll say this with all due respect, I want to make VMS look more like Linux than Windows. So we picked the Linux one, though to be honest, without boring, the details, the Windows one actually fits the VMS one a little better because it actually has a calling count, but we will show you how to do that. So we did that. The weird thing with this calling sequence, for performance, it will sometimes, if you haven't set a structure, well, I don't have an example or not, a structure with two integer fields. This calling convention will take those two integers, push them together, and put them into 164-bit register. So you have the compiler, LLVM, packs all those arguments together, and then at the prologue of the other end, explodes them all apart. Because remember, my talk the other day, yesterday, x86 doesn't have a lot of registers. They want to be fast as possible, so let's squeeze things into registers. It gets even worse if you have a structure with two integers and two floats. The integers get squeezed into an integer register. The floats get squeezed into a bigger floating register and packed that way. So you can't really iteratively go down your argument list like you used to do anymore. So if you have a C program, we make it work for you. On VAX or Alpha, it's easy to iterate down the argument list and look at them all. If you try to look at the real argument list on x86, it's not like that, but at the top of every routine, if we see you doing that bad programming, we will make a local copy of all those parameters for you to loop over, just so you think it looks like it would work. Like I said, we did have to add an argument count. In Linux world, routines don't have argument counts. If you pass 3 parameters, your caller better expect 3 parameters. And if you pass them wrong, you're in trouble. You can do ... in C and do VAR, standard arg, but that isn't just an arg count. There's an entire separate data structure that goes along with an arg count VA count. But we wanted something, I needed bliss to work. I needed macro to work. They're not C compilers. They don't know about VAR. The other one I'll mention, we have, remember on the alpha registers, I talked yesterday about the macro compiler. Macro has essentially argument registers 0 through 31 that it presents as what looks like hardware registers, because they were hardware registers on alpha. They were hardware registers on Regan. They're not hardware registers on x86. So we had to describe them in a slightly different way, but if you're unwinding or you're in the debugger, they look like real registers. They may be in memory, but if you unwind, I have to put them all back. If you walk your way back up the stack in the debugger, walk back up 3 frames and ask it what's in register alpha R5. It has to know where the compiler left them all. So the compilers leave information all the time for debuggers and the unwind system to say, where did you save all your registers at? And where in the code sequence did you save them? And where in the code sequence did you put them back? All that stuff is recorded, and it's been that way forever. On alpha, it's in the image file. On Titanium, it's in the image file. x86, it's in the image file. And it's not a VMS thing. It happens on every Linux box on the planet. Right? So you can go do an object dump or an elk dump on your favorite Linux box, and if you dig deep enough, you'll see the same, what I'll show you today, it's on every Linux system. So it's not new for VMS. We just have to understand it for VMS. And the other one is to go back to the VAX days. People who remember the VAX architecture, you had operands that were relative to your current PC, but a byte offset from you, or a word offset away from you, or a long word offset away from you. There's 3 different types of operand modes, because VAX tried to squeeze the instructions as small as possible. Remember, those are the days where every byte was precious. The first VAX is shipped with, 256 kilobytes of memory. VMS would run in 256 kilobytes of memory and let users log in and do things at the same time. Probably not many, but you can do that. Right, the very first VAX is 780, its maximum memory was 8 megabytes. I make data structures bigger than that these days, right? We don't, so all of the stuff that happens on VAX, and it's even historically what we still do in compilers today, is because 40 some years ago, we had machines with no memory, slow machines, slow small disks, and a very slow network. One of the things that we are dealt with here on Linux versus VMS, I hinted yesterday, is I still have to leave the stack in 32-bit space. I cannot move the stack. I mean, there's too much code on the planet, all the macro programs that want to push and pop things on the 32-bit stack. And then you put things, all the descriptors on VMS that have 32-bit pointers buried in them. I can't tell everybody to stop using descriptors or change all your code to use different 64-bit descriptors. That's just not reasonable. Okay. So we had to come up with a model for VMS where everything is code, and we put code in 64-bit space, so we wanted to make more room in 32-bit space for bigger heap, for bigger data structures. So I moved all the code to 64-bit space. But so if you look in the AMD calling standard, which I think I have a pointer here somewhere, I don't know. They have a couple different memory models. They allow you to do non-position independent code, where you have code that loads a particular address in memory and it's statically all linked together. We don't support that. Everything from VMS is position independent. They have one that all the code and data has to live in the same 2 gigabyte address space. Well, if I put code in 64-bit space and data in 32-bit space, that's bigger than 2 gigabyte distance from one to the other. So I can't do that one. The large model is everything can be 64 bits everywhere, but the x86 only has 32-bit relative offsets and 32-bit jump operands. So the large model makes it difficult. So we end up with a merger of all that. I have to leave it. No code segment on VMS x86 can be bigger than 2 gigabytes. So don't write more than 2 gigabytes of code. So, I think you're okay there. I think Vitaly can come close to 2 gigabytes of code if you give him some coffee. But the data can't be more than 2 gigabytes, but they can be more than 2 gigabytes apart, which is different than most Linux people can think. So we did some work to make that happen, because that's how I can give you the best of x86, but still give you 32-bit stack and 32-bit descriptors. I mentioned where this unwind data is. Again, it exists on every target, on every Windows machine, every Linux machine, on VAX, on Alpha, on Itanium. Is every routine, the compiler has to leave some information on where did we save any of the registers and where did we put them back. Because the system needs to know, if you're unwinding, where is the current register R5? Did I save it on the stack, or is it still in R5? Or at the bottom, as we're unwinding out, is R5 been put back in or not? And if it hasn't, if I'm unwinding, the system has to put it back in for us, because you're skipping, if you're unwinding, doing a set jump, long jump, for example, and if you're skipping the ends of the epilogue of a routine, no one's there to put those registers back. Right, so the system has to find them all and put them back for you. Again, we just use the EH exception handling stuff that comes from Linux. I will warn for people in the back, coming up on some slides, I do have screen grabs of some stuff from linker maps. So you might have to pull out your binoculars or switch up a little bit. But the format of these things is the same from Linux and used on VMS, but the way you access them on Linux, you might use something like the libunwind library package. They have these structures for exception handling to talk about machine state. But on VMS, if you're used to writing VMS condition handlers, you get things like signal arguments and mechanism arguments for each routine. We wanted to keep the same behavior. So the SIG-args is exactly the same on every platform. The mechanism array is different on every platform on VMS because it lists hardware state. But we had to take all the stuff from Linux and put it into a hardware state that feels like it came from VMS. I think the other day, if you were in Norm Rostevika's talk, he said the first manual you should read when you're porting VMS, an application on VMS, is read the calling standard. I disagree. Don't read the calling standard. It's boring. It'll put you to sleep. The calling standard is useful for a couple things. If you want to know about all the VMS descriptor types, you see all these weird things of class S descriptors, class A descriptors, and if you want to know what they really are and what they look like in memory, the calling standard describes all that. They're not target specific, that's just a software interface. So half the calling standard talks about that, that's useful. Half the calling standard talks about what the mechanism array looks like, that's useful if you have a condition handler. The other half of the calling standard talks about all this junk of which register is used to pass which parameter and all this exception handling data. You don't care. If the debugger works right and if the system works right, you don't care how the compiler told the system where we saved all these things, right? And somewhere in there it's pretty big exception handling data. We'll see in that, like if you read enough documentation, and then the calling standard, we've actually documented 2 exception handling formats. You see in the Linux space, there's the one that Mac OS uses, which is a Linux derivative, essentially, the Unix derivative. We've documented it. You'll see things in there talking about the compact form of unwind data. So if you read the calling standard, and if you aren't that brave, it talks about some stuff that we actually haven't implemented. But I don't think we say that anywhere, that we don't implement it. But just to warn you. Again, if we did our job, you don't care how I recorded it. It can be magic. I talked about that memory model stuff. I just got ahead of myself there. There is a YouTube presentation. Follow that link. You can see me 5 years ago. And there's the link to the current. If you really want the current x86 ABI, the full thing that we use. So we took that document, the one from GitLab, and that's what we started with. And then we took that, put it into our calling standard manual, make it look like a VMS manual, because there's a fact chapter, alpha chapter, ITA chapter, x86 chapter, but almost all the words we took came from that manual. So I kind of talked about that, but we had to worry about where all this stuff goes. And because of that, the linker has to worry about where all this stuff goes. One of the things I think, let's go next page. So on VMS, when you want the address of a routine, how big is it? On alpha, it was the 32-bit address of code, right? On X, 32-bit address of code. On alpha, it was the 32-bit address of a procedure descriptor, which is an opaque data structure that has a bunch of stuff in it, which is including the unwind data, what can save where, and pointer to the actual code. On ITA, you got a 32-bit pointer to this function descriptors, similar behavior. Where's the real code and where's the real data, that linker data that goes with it? On x86, no such thing. It feels like a VAX again. So the address of a routine is the address of the first instruction. That's all you get. Now, that code, I said, well, I wanted to put code in 64-bit space. That would mean that the address of a routine on x86 would be a 64-bit pointer. That's not going to work. How many system interfaces out there declare exit handler and other stuff that assume that the value of a procedure, its address, fits in 32 bits? How many Fortran programs out there that do %loc and grab the address of the routine and shove it somewhere? How many C programs take the address of the routine and shove it into a void star 32-bit pointer? So how do I get 64-bit code that is reachable with a 32-bit address? The linker makes trampolines. So every time that there's the address of some routine is the address of a 2-instruction trampoline in 32-bit space that bounces you to the real code in 64-bit space. So the linker has to manage all those. I'll show here in a second. Because of that, we have the linker makes the trampolines. And again, I have to worry about how far we can reach with every addressing mode computation, only 32 bits away. That's why there's a 2 gigabyte limit on those things. And then you'll hear the reference to GOT, global offset table. It's just a linker generated table of addresses. So when the compiler says, I need the address of some routine, put it in the table. Linker says, sure, I'll put it in the GOT. And then I'll say, and by the way, can you give me the relative offset from the instruction I'm sitting at here to that slot in the GOT? Always a fixed offset. And then the code can say, okay, I don't know where the real address is, but you promised me that if I go that many bytes from where I'm at now, I'll find a quad word that has the real address in it. And then the linker and injector fix them all up. Again, not much different than what you see on Linux. The Linux has a GOT. The Linux loader fixes them up. The whole idea of having fixed subset load time is not unique to VMS. We probably have a few more fixed subs than your average Linux box. And since we always require position independent code, we have probably more things on. On Linux by default, if you write your little hello world program with GCC or Clang, it's a small memory model, non-position independent. They just link everything together. You get a really small image. There's probably not many fix-ups, but the moment you want to try and write anything real, besides hello world on Linux, you'll get fix-ups on all the things. And again, I have to call, again, you can imagine on Linux, if everything is jammed into a 64-bit address space, you can just say, well, so the on x86, the call instruction is one of these, the operand. It's not a raw address, it's how many bytes forward or how many bytes backward, so relative offset. So the call instruction in x86, the linker can say, okay, you're about to call a routine, it's in your image, it's this many bytes forward. I can just go, I'd say, well, go straight there. But what if I want to call a routine that isn't in my image, right? So start queuing them, libdol or something. So again, the linker has to make, and we do this on Itanium as well, has to make a small trampoline And so the call instruction is call there, and what you'll find there is about 3 instructions that actually jump to the real code, because it's 64 bits somewhere, but calls are, you may have a pointer, a function pointer in C, and I want to do a call. So there's all these little trampolines created by Linker all over the place. Here's your first eye chart. We can see here, so this is the program, these are the pieces of the program when it's being loaded into memory. This is an analyzed image output. And we can see here that there's certain pieces of the image. There's a chunk that's at base address 2000 hex, that's in 32-bit P0 space. There's some stuff there. It's all those 32-bit trampolines that the linker created. The next one, segment number 1, which is read-only executable. That's a quad address. You see it's an 80 million address. So quad, there's a bunch of zeros, and then 8 to that does a P2 address. That's the start of the code. Okay, so that's the read-only executable. That's where we put all the code for this thing. At a fixed offset from it at 8 million and 80 million and 2000, we see that fixed offset and the unwind stuff. Those are all, that one and the one below it are the GOT. All this exception handling data also has pointers back in the code, and the code, they're all relative pointers, but they have to be at the same offset. So wherever this code for a main program, it's going to load into memory here. But imagine you're making a shareable image, and you're linking a shareable image. The linker just knows that link time relative to the start of the image. Whether I could have done this on the CRTL, and the linker said, okay, I've picked a base address as where I think the CRTL code might be. It's never there. When you load your C program, all these RTLs get loaded. CRTL get loaded somewhere else. And so the linker and image activator have to readjust all these pointers to get them to match them. And then down there, segment 4, also 32-bit. So there's two segments of linker generated trampolines. But that's the easy one. Those you can see some of that here. So if you see this, if you're actually looking at linker maps, if you are, please, I apologize for doing that. Don't. I hope you never have to look at one at this level. The fixed offset keyword is something you've never seen before. This is as we told the image activator. These have to. You can put them anywhere you want, but they have to stay the same distance apart. Because all those relative addressing things have to stay the same. And if you still have a VAX laying around somewhere and look at analyze image, the format's a little different, but the same thing happens there. You have to keep things fixed also. Right. Here's the harder one for you for an eye chart in the back. I was showing you all the different PSECs of how things got loaded and put together, but you can work your way down and see the code, but there's like at the top, you see that the linker $code, that's all the linker generated trampolines. Way down at the bottom, you saw that linker GOT, that's where the global offset table is. Those are the map of those 2 segments that we saw in the image. I'll leave this to you if you want. When the slides are available to read through them, but there's pieces scattered everywhere of linker generated trampolines and code. You probably have never seen much of it before. And if you really want to look at code, you can see this is the output of the analyzed object disassembly. And you can see there like a call to some Pascal RTL routine at PLT. PLT is the name of the relocation program linkage table, I think is how they call it in the Linux standard. What there really is an offset to the trampoline that will eventually bounce you to the Pascal RTL. So the linker makes the address to the trampoline. If you look to the code, we can't tell here in the object, but on the left side, you see the 4 zeros and the E8. The linker will fill in those 4 zeros with the offset to the trampoline. If you dump out the trampoline code, and I have an example here in a minute, those addresses of different shareable images, they have to be filled in by the image activator, so you can see it. So here's the simple program. If you look at the generated code, that's the same thing. And then at a fixed offset after it, you see all those little AD, add byte instructions, those are just zeros. That's how analyze object disassembly, the opcode 0 in x86 is the add byte instruction. So it just gets tricked into thinking that. But down there at the bottom, there's a bug at the very bottom two lines. It's actually one of the trampolines. It's just a jump to a 64-bit offset somewhere else. So there's an actually analyzed object disassembly gives you a hint of where it's going to jump to. And if we went to those addresses, you would see even more traffic. So the linker has to manage these. The linker caches them. So if you have a program that has 1,000 calls to sysqio, there's only one trampoline. Doesn't make 1,000 trampolines. And when it all gets linked together and merged together, there's only one at the final end. It doesn't. Used to, back in the early Alpha and Itana days, you would have 1,000 of them. And it made the programs quite large. I don't remember, there was one point we told everybody to relink all your programs, and not because they were broken, it made them smaller. I remember relinking one of the compilers when the linker finally learned to compress them and only use one trampoline. It like made the C compiler like 30% smaller. It's like, really? The C compiler was 30% duplicate trampolines. So yes, it was. But you could, again, nobody should be doing analyze image segment equals code and looking at the generated code. I don't want to do that, and that's my job. So you can, but it's all here. You can find it all. You can see all that. Analyze is your friend. But again, the equivalent tools on Linux, if you want to use OpsDump, a couple of those, you can dig your way through any of this stuff. So beneath that boring stuff, what the routines that people would maybe use in the Kong standard, if you actually wanted to do some stack walking, maybe you wanted to walk back up the stack and do something, maybe examine, again, you're writing C code. Do you know what's in some hardware register? Do you care? You don't, right? Only the C compiler picked the register for you. Why do you want to know what's in REX? I don't. So, to be honest, walking back up the stack and getting and looking at hardware state is only really useful to people like the debugger, maybe, or if you have a really fancy condition handler. But even then, I don't. Usually you walk back up the stack and you're just asking, okay, who's the return address? Can I go one more? So. Why call them? You can call them, you can't. Now, one of the things you can do is the useful thing is, this is some of the low-level routines that like set jump, long jump would use, or Pascal's nominal would go to. And so these invocation context handles is with the pointer to the frame on the stack, and you can look at registers if you want in the mechanism array, or the invocation context block, which is an equivalent data structure. But it's useful to get the address of something that you want to then maybe unwind to, or again, such a long jump out wants to unwind back to it. There's a handful of these routines. So these are the ones almost anybody would call it. These are the ones I see called the most in any type of handler. And when I say the most, in like 5% of handlers, most handlers don't even do this stuff. But they're all there. They look just like the Itanian equivalents, and these are all documented in the calling standard. Again, you can find them all. They tell you what the arguments are. I've never called them. But this is how you can get that. One of the things I've seen people want to do this, so I get to now is I'm writing my own application, and what I really wish is I wanted to know what my call stack is right now. And historically, you're sitting there in your program and think, oh, I wish I could know what my call stack was. Well, one way you can do is, people don't know if you can do if you have a program that's running, including one that might be infinite looping or waiting on some input, you can type Control-Y, get back to the $, and type debug. Up comes the debugger right where you're at. So you can do a Control-Y, debug, the debugger comes up, you can do a show calls, say, oh, that's where I'm looping in this code, and you can just debug it. It's just as if you were in a kept debugger all along, and you can step, call, and you can just say, go and continue program execution. So that's one way of knowing where you're at. If you want to do it through a program, let's say you're going to grab your call stack and put it into a log file. Well, it's kind of hard to do that, though you can, I don't know, people, I'll give another tip. So in your program, you can signal $$_debug. So in a program, you have a point, you can say libvar signal $$_debug, it'll come up with a debugger. And if you give it optional parameters, you can say, libvar signal $$_debug, comma, quote, and a string, show calls. Come up with the debugger, it'll do the show calls. You can do multiple line commands on that debugger command line. Show calls, semicolon, go. Come up with the debugger, do a show calls, program executes again. So you can catch your show calls in your program over and over and over again. It just comes out the output. So you'll let the debugger do it for you. So you don't have to dig your way through what routine am I in, who called me, look up the name, print the name out, let the debugger do it for you. But if you want to do it yourself, you would use these. I don't know if anybody knows there's actually a callable interface in traceback. So if you want to walk back up your frames and ask for things like what's the name of the module, what's the name of the routine, what line am I on, what PC am I on, the traceback utility inside of VMS uses these routines. All it does is use those $$ calling center routines, walk up a frame and says, and these routines take a frame handle. They take one of those invocation context blocks saying, dear callable traceback, here's a routine, tell the information about it. What file name did it come from? What module name is it? What line am I on? And that's exactly what traceback then turns around and uses and writes the line in traceback. So you can write your own traceback if you want. So if you wanted to do those routines and take those outputs, put it into a log file, a mail message, something, and send it back to System Manager or something, so you can encode your own stack walking. And so, to be honest, when I see people that are using those calling center routines to stack walk and look for who I am, I said, what's your real problem? They go, oh, I'm trying to find the name of my caller because I want to print it out somewhere. So, well, do you know we have these routines? These are probably the interface is weird. It's in the manual. There's examples in the utilities manual. I think the examples are actually written in C, which makes them useful. We had the tendency over the years, we would give you examples in the manuals. We'd give you Bliss examples. You're like, why would you give me a Bliss example? We were just trying to hit every language. You still may see examples in some of the manuals that we still give PL1 or ADA examples. And you're saying, okay, where's the PL1 compiler or ADA compiler I would use to compile this example? And they said, yeah, no. I think that would be a good exercise for somebody new to go through all the manuals and find all those old PL1 or ADA examples and just rewrite them into C, please. Shouldn't tell you, I should be talking to the people that work with it. So, but you'll still see, but we tried the examples of a callable traceback. They're in there, they're in C. I think I don't know for x86, I remember on Itanium, I might have been the one who wrote the example. So I know it worked then, but I should go back and not embarrass myself and make sure it works for x86. I think so.
You put this stuff to fit the whole traceback into one line.
Okay.
So that it's compact.
Yeah, okay. Well, good. One user for that. Yes, you can, whatever format you want to use to squeeze them into. So that's of all the callable interfaces of the calling standard. In my opinion, this is between the calling standard routines and the callable traceback are the only useful things that you should get out of the calling standard manual. And this one isn't. This is in the utilities manual. So there's, anything else in your calling standard manual before you're either lost or you're trying to figure out a descriptor format. But the rest don't read the calling standard manual. So I think it's probably one of the better written manuals we have. It has to be the one that's most accurate. So that is, I believe I have read that manual front to back 20 times more. So, so at this point, I'm kind of done with the behind the scenes. I had a lot more link map or machine listing examples that I didn't want to bore you with because I was getting bored. I figure if it's boring me, nobody here wants to see them. So anybody have any questions? I'm happy to take questions, but at this point, you shouldn't. Don't have any questions. Yes.
I've got a module which is written for 64-bit Linux in assembler, and that has the Linux the exception handling as directives in it. Will those work on VMS?
If it has a hand, yes, if you take that assembly file, our assembler will generate the same EH data.
Excellent.
And in theory, all of the routines we have, so inside librtl and all these lib$x86 constants, we actually took the lib unwind from a FreeBSD system and we brought it to VMS. We changed the name of some of the routines and we've made the interfaces look like SIG array, vector array. Under the surface, if you look at the code inside of librtl, it's lib unwind, just from a Linux box.
One other question, do I actually have to pass the argument card in LIX?
Do you have to?
Then they're going to go over because the code I've got doesn't need to on them.
No, I mean, to be honest, we always put the argument count in that other byte in racks because I don't know who's going to use it. Yeah, there's many places you don't. And matter of fact, as optimizations, the compilers, like when they're calling some of their library routines, I have a table inside. I said, look, I know that some Fortran RTL routine or CRTL routine doesn't need the R count. I can skip it. Now, what I do though is the moment I skip that R count today, then in 5 years, when Vitaly wants to add another argument to a routine, he goes, I'll just check the R count to see whether you passed me 3 or 4. And then he finds out that 5 years earlier, I decided not to bother with the R count. And then he gets very mad at me. So we just pretty much pass it. It's almost free to pass that R count.
You have our own compiler which basically calls into a runtime system that we see.
Yeah.
At the moment, it doesn't pass the other count. Well,
Okay.
I can put that in.
But most things don't, but yes, you'll see in there, it's a, racks, and we use the second byte. The first byte is part of the real function, known as, well, you use the second byte. And am I cheating? Are we going to get caught? Is this someday when they extend the real AMD clock standard to use that second byte? What happens then? I plan to be gone. But I don't know. Because if you go to that GitHub and look at the edit history of that, the AMD 64 calling standard, I think it was last updated like 14 years ago. It was quite stable. No one is changing the calling sequence on Linux today. They just know better. They would not change their own calling sequence. They would invalidate every Linux box on the planet.
Thanks.
Rob, what do you want to know about BASIC?
So would you like to discuss a real world example of unwind data and exception?
Sure.
And what happens when it's not quite right?
So what Rob is referring to, we had a customer using FMS, and on occasion it would crash. Acquia, they're waiting at some screen, some timeout happened, and the code in FMS says, I want to do an unwind. I'm tired, I'm bored, the customer is responding, I'm going to unwind back to the main routine and refresh the screen or do whatever FMS does. I don't know what forms do. And it would go back and it would acquia, because in Bliss, our Bliss code is using some of these alpha pseudo registers. And the compiler along the way, the Bliss compiler saved some of those alpha registers into some stack location. And the unwind was intended to put them back. On alpha, they get put back. On titanium, they get put back. We forgot to generate some of that exception handling data. So the unwind code in libunwind didn't know to put them back. And so when it got back to the top level in FMS, what was in that register? I don't know what was in that register. Some pointer to some FMS internal data structure was not the right pointer. And it took a long time to figure out what was going on. And then again, I could bore you, but on how to read unwind descriptors from analyze image, and we saw that it was missing that data. And we put it in and it magically worked. What do you know? So yes, but the point is that the compilers, we save a lot of information on prologues and epilogues in the dwarf. There's potential in some of the other dwarf standards that also There's information on every call site, so a debugger can do additional debugging around call sites. We sprinkle information everywhere. So if you look at a program on x86, people say, well, the instructions are smaller in x86 compared to like Titanium. Is my program smaller? And just from looking at the sheer exe size, you'd say, well, it's a little smaller, but it's not as small as I thought it was. Well, half of an image file these days is not code. Half of it is all these linker generated tuple routines, all these global offset tables, all the collected exception handling data. Things like EH data and debug information are not read from the disk. So you can have an image on your disk that is, 50,000 blocks big, but image actor only reading the code of the data when you start it. All the dwarf, it doesn't touch it. The only person who needs the dwarf would be the debugger. The debugger brings it all in. Or if you're going to do exception handling, it'll bring it all in. So there's a deferred load, so you don't really have to load it all in. But yeah, if you just look at the size of an XT, it's hard. You can do a checksum/image. You can kind of see maybe which segments have code in them. We saw that listing earlier from the map, which segments have code. You can look at your map file and compare code executable segments, alpha to Titanium to x86. And it is smaller, it's a denser instruction set for sure, but looking at exercise. You can't see it because we generate more exception handling data and dwarf information. So it's more flexible, but it's a bigger image.
There is no user interface for accessing this dwarf information.
Correct. If you want to dig your way and pick through the dwarf of an image, that
I'm interested in finding the special variable by name, for example.
yes.
The program.
I'll write that down. I mean, yes, we don't have a good way of iterating through the dwarf at that level. I mean, but that's exactly what traceback does, for instance. It reads through the dwarf and says, okay, I'm looking for all the routines in this image, and then looks at all the PC values with the callable traceback and say, oh, this PC value is inside of this routine. I now need to print this routine, formatting it on the traceback line. So traceback actually reads all the dwarf and skips over everything that's not a routine. So it sees the variables and uncovered variables. But I can say if you wanted to do that, I'll let Tim know. Any other questions? Well, thank you for wasting your time here with me today.
If I'm one of the few people who really does need to know.
Yeah, so some people do.
Yeah, we've got this compiler which doesn't use object models, it just compiles on the fly.
Yeah.
Map code into memory,
Yeah.
executes it,
Yes.
it makes call to the C runtime system.
Yes.
So it has to know how to do that.
Correct. I think later say Anders Johansson's talking about ACMS. ACMS does the same thing. It makes code on the fly.
RDB does as well.
And RDB does as well.
Yeah.
And so you have to. There's a couple system calls you have to write.
You have to declare. You have to
write in the master unline table to give the addresses for this routine at these addresses. Yes, yeah. And you've already given the exception handling.
And we have to tell it it's legal to have a PC in that range, don't we?
Yes, we do.
There are calls for that, I think.
Yes, there are.
Yes.
Yes, there are. I don't know how well documented they are, but they are in there, and I think those are also in the calling.
We used them on Alpha.
Yes.
We didn't quite get that far with the training. We were doing the fork when it became obvious we didn't need to.
Yeah.
And,
the other thing I haven't talked about at all for compiler features, LLVM has a lovely JIT compiler, so you can do really good code generation on the fly. And the same thing for JITting. Could you do that? And then I have to make sure all those addresses get registered correctly. One thing we have noticed on Linux, so optimization wise, you can imagine the best optimizer gets to see the whole program. Yes. You get to see all the modules, to see who references what global variables. On 264 Unix, we had like a whole program mode where you would give the linker all the objects. On VMS, the linker doesn't look at that level. If you look on LLVM and Linux and their linker, what you do is you generate not objects from the compiler, you generate bitcode, the LLVM intermediate files, and you give them all to the linker. The linker then hands them all back to the LLVM JIT and it JITs them also. The code generation doesn't happen in compile time. The code generation happens at link time. But now the linker can see all the code for all the modules and the optimizer can see all the code for all the modules and what you thought was a global variable and an external variable. Now I know it's, yeah, you're the only two that use that variable and now it's static. I don't have to expose that and I know exactly who uses what and you get some really good code out of there. And so I mentioned that to Camille once, is do you ever want to think we would maybe use that model on VMS? Because in certain applications, for your average hello world program, no one cares. But for Google or somebody who has a very large thing or a database provider might say, you know, I might want to benefit from having all these things together and having one master optimizer to get it, because I think Google, it's called LTO in the terminology on link time optimization, but it's link time optimization and code generation. On whatever application Google does, and they won't, Google does so many things. They're listening right now to my, they were getting, you know, they were getting, you know, 10, 20% performance improvement. But as you know, benchmarks lie all the time. I can write you a benchmark that all it does is, you know, do a database query, you know, 20 billion times over and over and over again. I can optimize that, but no real program does that. Maybe most real programs don't do that. But yeah, I'm wondering at some point, should I try to think about putting more of the stuff into the linker?
That's interesting. I mean, on Windows, you can say when you're compiling that, oh, I want to do a global compile at link time. So you kind of do a flag, and then the linker does things.
So LLVM has a lot of infrastructure behind this that I've not ever mentioned. There's various sanitizers looking for, you know, memory overwrites and type mismatches, but there's a whole thing of doing link time optimization.
Interesting.
Would help 5 VMS users on the planet, but you might be one of them, right? And again, how much time, how much effort is it? Because I think it'd be a lot, because I now don't, I wouldn't have to learn how to keep object files in an object library. I would probably wrap the intermediate LLVM, because object files are just ELF files. ELF files are just containers, they're a bucket. And I probably would, and that's what happens, I would take that bitcode stuff, put it into a ELF file, put that in the object library. But I'd have to teach all the tools that when you pull out that object, that it's not really an object. It's something masquerading as an object. So I can do it, but I think it would take several people a long time to sort out all the details. And again, it depends how happy you want to be.
Yeah, I don't think it would help AI because I'm not sure LLVM.
I will try.
Basically conflict in our language.
Yeah.
Our language is both got decision tables, and it makes it
a
little odd.
Yes. And again, I don't know how I would ever, there's models in VMS, there's things that probably wouldn't work with, but yeah. But the one of the things I want to do is all the LLVM that comes with a lot of tooling, besides the code generator, there's again, the JIT, you can, you know, I want to provide all these tools. It's part of my build. So my goal is for the LLVM side of things, I want to, like I said, I've only changed a couple thousand lines at most. I want to give all the code. I want to tell you how to, if you want to build your own LLVM backend, if you want to make your own compiler using my LLVM, you can. If you want to, whether it's your domain specific compiler or whether somebody wants in their spare time, if Gerard wants to go make an ADA compiler, or somebody wants to put Rust or any of these things on VMS, I can enable that. And give that stuff that way. Because and all the other tools, LLVM comes with their own version of objdump and their own version of elfdump. You don't have to go find some GNU distribution and build it yourself. I've built it for you. And because it's like, there's things I couldn't give away. If anything has an HPE copyright, then we're kind of bound by this contractual agreement with HPE. I can't, you know, can't you open source something? It's not really mine to open source. The Bliss compiler. Bill says, it's a Bliss compiler. Why don't you open source the Bliss compiler? I would love to do it. It's all those HPE copyrights at the top of every module that keep me from doing it. And I know at one time Johan Gedda was talking about, you'd ask him, says, you know, because you've heard his talk on how, you know, at times he's given money to, you know, to HPE, we get the access to the code, we gave money to get to the support contracts, he gave more money to get some of the support people. He said, would it be worth my money to buy the IP outright from HPE? He said, I'm sure they would quote me a number. He said, I probably would fall over the heart attack. But if you ever bought the IP from them, then what do? You go through all the files and you delete their lines. They've given you permission, delete my copyright from all those files. It's yours. Take it and be happy with it. But I have no idea how much that would cost. That's what that would a lot from HP for a lot. I mean,
If you delete these lines, they would never notice because they have in the reference copy to check it.
they don't, and that's the question now. I mean, we're such a small thing. Does HPE, I mean, I'm sure at some high level they care about royalties, whatever, pay them. But if I took like the Bliss compiler and put the sources on the internet, HPE is not losing any revenue. And it's not like there's anything in there that's patentable or value of intellectual property that I'm letting out for free. It's like so there's some things every now and then make sure this microphone is off. I have accidentally sent mail to people with a listing file. People want to know something, like I'm struggling. I'm calling some library routine and it's returning a weird error. And the manual isn't good enough. If I could just peek at the code for 5 minutes, I'll be really happy. And I will sometimes accidentally send you a listing file, knowing that one listing file by itself, I'm not giving you the entire operating system. You can't build it, but here's the listing file. And technically, I've been told several times you shouldn't be doing that. And between us and other people, it's like, I don't care, because I know in the long run it doesn't matter, right?
I remember the days when you got back VMS with the props of microfiche.
Yeah, the
And you
microfiche.
had
Yes.
listing everything.
Yes. Also. And as a customer, I remember typing code back in for the microfiche.
I think a few bugs all deck about.
Yeah. So I know
I didn't want to use event flags after reading the microfiche.
No, there's things like, please, be careful reading these. You might end up with a horrible trauma.
Some parts were really nicely structured, but
And there's
others,
I think there's
impressed.
still a bug in the librarian routine, that if you wrote something which isn't the
I
library.
was doing my
with the
military
LBR,
service.
Uh-huh. Yeah.
And I
It's
just
not a
got
library,
these,
you
so
lose
I
control.
actually had some
Okay.
time
If
to
you get
read
too close.
through.
But that was there certainly last time.
Was a useful
Oh.
management.
That would-
Exactly.
Librarian LBRs are kind of, there's places in there that are well written. There's like, places in there that it's like,
We
I
use
don't
the
want to.
library call.
Yeah. Uh-huh.
I have a question.
Thank you.
You know, when I don't remember the name exactly, when you have extended memory, when you're compiling for 64 bits
Yeah.
and you have data structures that are huge.
For Tremor, it should put common blocks in 64-bit, static common blocks.
Yeah, but I mean, you could map memory in.
Oh, yes, you can. You
64
can do
bits.
it.
I think we're doing this with the database